Imagine floating in the absolute darkness of space, 3.5 billion light-years away from everything you have ever known. There is no sound here, no air, no warmth from any nearby star. You're suspended in the void between galaxies, in a place so remote that the light reaching your eyes left its source when the most complex life on Earth was still single-celled organisms swimming in primordial oceans. And then, slowly, you turn your gaze towards something that should not exist. Something that defies every intuition you have ever had about how the universe works. You see a galaxy, a massive spiral of hundreds of billions of stars, but something is terribly wrong. At its center, there is a light brighter than anything you have ever witnessed. A brilliance that outshines all those hundreds of billions of stars combined, not by a small margin, but by a factor of 100. And as you watch, as you observe this cosmic scene playing out across millions of years compressed into your perception, you realize that this galaxy is dying. Not in the gentle way that galaxies usually fade over cosmic time, but violently, catastrophically, being consumed from the inside out by something so powerful that it treats stars the way a whale treats plankton. There is a monster at the heart of this galaxy, an invisible beast of pure gravitational fury, and it is eating everything. This is the story of a black hole that is devouring its own galaxy, and what it teaches us about the most extreme physics in the universe. What if I told you that somewhere out there in the cosmos right now? As you listen to these words, there is an object consuming matter at the rate of 1 Earth mass every single second. Think about that for a moment. Every second that passes, every beat of your heart, an entire Earth worth of material is being crushed, heated to temperatures beyond imagination, and swallowed into an abyss from which nothing, not even light itself, can ever escape. What if I told you that this cosmic glutton is so massive that if you tried to count from 1 to its mass in solar masses, counting one number per second without sleeping or stopping, you would be counting for over 300 years? What if I told you that the energy being released by this feeding frenzy is so immense that it produces more light than 1 trillion suns, making it visible across distances so vast that the light has been travelling toward us since before life crawled out of Earth's oceans onto land? And here is the question that should send a chill down your spine. Here is the thought that keeps astronomers awake at night. Could this happen to our own galaxy? Could the relatively peaceful supermassive black hole sitting at the centre of the Milky Way, just 26,000 light-years from where you are right now, could it wake up one day and begin consuming everything we have ever known? Before we dive into this cosmic horror story, before we explore the science and the spectacle, and the terrifying implications of a galaxy being eaten alive, I want you to do something. If you have ever looked up at the night sky and felt that sense of wonder, that curiosity about what secrets the universe might be hiding, take a moment to subscribe to this channel and join our community of cosmic explorers, and I want to hear from you. Drop a comment right now telling me what you think happens when a black hole gets this hungry. What do you imagine occurs when the most extreme object in the universe goes on a feeding frenzy that lasts for millions of years? I want to see your wildest theories, your most creative ideas, because sometimes the most profound insights come from unexpected places. Now let us begin our journey into the heart of darkness. To truly understand what it means for a black hole to eat a galaxy, we first need to understand what a black hole actually is. And I do not mean the simplified version you might have heard before. I mean really understand it in a way that will fundamentally change how you think about space, time, and the nature of reality itself. A black hole is not a hole at all. It is not an absence of something, not a gap in the fabric of space. A black hole is a region of space-time where gravity has become so extraordinarily strong that nothing can resist its pull. Imagine taking our sun, a massive ball of hydrogen and helium 1.3 million times the volume of Earth, and crushing it down to a sphere just 6 kilometers across. All that mass, all that matter, compressed into a space smaller than a city. The density would be so extreme that the very fabric of space-time would curve in on itself, creating a region from which escape becomes mathematically impossible. The boundary of this region is called the event horizon, and it is one of the most fascinating and terrifying concepts in all of physics. The event horizon is not a physical surface. You cannot touch it. You cannot see it directly. It is simply a boundary in space, an invisible line that marks the point of no return. Cross the event horizon and you are doomed. Not because something will grab you, not because you will hit a wall, but because the geometry of space-time itself tilts inwards so severely that every possible path, every direction you could travel, even if you are moving at the speed of a light, leads only toward the center. It is like being on a river that flows toward a waterfall, except the river is time itself, and the waterfall is a point of infinite density called a singularity. The singularity is where our understanding of physics breaks down completely. It is a point where density becomes infinite, where the curvature of space-time becomes infinite, where the equations of general relativity produce answers that include infinities, which is nature's way of telling us that we are missing something fundamental. What actually happens at the singularity? Does matter cease to exist? Does it compress into higher dimensions? Does it tunnel through to another universe? These are questions that our current physics cannot answer. Questions that will require a complete theory of quantum gravity to resolve. For now, the singularity remains the ultimate mystery, the final darkness at the center of every black hole. But here is where things get really interesting, and where we begin to understand the monster we're dealing with. Not all black holes are created equal. They come in dramatically different sizes, formed through different cosmic processes, and their behavior varies accordingly. The smallest black holes we know of are called stellar black holes, and they form when massive stars die. When a star at least 20 times more massive than our Sun reaches the end of its life, it has burned through all its nuclear fuel. The outward pressure that has been holding the star up against the crush of gravity suddenly disappears. The core collapses in on itself at nearly a quarter of the speed of light, and the outer layers of the star explode outward in a supernova, one of the most violent events in the universe. What remains at the center is a black hole, typically between 5 and 50 times the mass of our Sun, with an event horizon perhaps the size of Manhattan Island. These stellar black holes are scattered throughout galaxies, remnants of ancient stellar deaths, cosmic graveyards marking where giant stars once shone. Then there are the mysterious intermediate black holes, objects with masses ranging from a few hundred to a few 100,000 solar masses. These are the missing links of the black hole world, and for a long time astronomers were not even sure they existed. They are too massive to form from a single star's collapse, but too small to be the supermassive giants we find at galaxy centers. How do they form? Possibly from the merger of many stellar black holes over time. Possibly from the direct collapse of massive gas clouds in the early universe. Possibly through processes we do not yet understand. In recent years, gravitational wave detectors have begun to find evidence of these intermediate black holes, catching them in the act of merging with other black holes in cosmic collisions that shake the fabric of space-time. But the true monsters, the objects that dominate the centers of galaxies and shape the evolution of cosmic structures across billions of light years, are the supermassive black holes. These titans range from millions to billions of solar masses. Our own Milky Way galaxy harbors one at its center, an object called Sagittarius, a star, with a mass of about 4 million suns. The famous first image of a black hole released in 2019 showed the supermassive black hole at the center of the galaxy M87, a beast weighing 6.5 billion solar masses. And beyond even these, at the extreme end of the spectrum, are the ultramassive black holes, objects so large that they challenge our understanding of how black holes can grow so big in the age of the universe. Some of these cosmic leviathans weigh more than 60 billion suns, with event horizons larger than our entire solar system. The black hole we're discussing today, the one that is actively eating its own galaxy, falls into this ultramassive category. It is not the largest black hole ever discovered, but it is among the most active, the most hungry, the most destructive. It sits at the center of its host galaxy like a dragon on a hoard of gold, except this dragon is not content to simply guard its treasure. It is actively consuming everything within its reach, growing larger and more powerful with each passing moment, releasing energy in quantities that dwarf anything else in the observable universe. But here is the paradox that makes black hole physics so fascinating. Black holes are supposed to be black. They are supposed to be invisible, dark regions of space from which no light can escape. So how can the brightest objects in the universe be powered by black holes? How can something that swallows light be responsible for outshining 1 trillion suns? The answer lies in what happens to matter before it crosses the event horizon, and it is one of the most energetic processes in all of nature. When material falls toward a black hole, it does not simply drop straight in. Unless it is aimed directly at the center, with zero angular momentum, which is almost never the case in nature, it will start to orbit. But this orbit is not stable. Friction and magnetic fields and gravitational interactions cause the material to slowly lose energy, spiraling inward like water circling a drain. As more and more material accumulates, it forms a flattened disk around the black hole, a structure called an accretion disk. And within this disk, something remarkable happens. The material is packed together so tightly, moving so fast, experiencing such intense gravitational forces that it heats up to extraordinary temperatures. The inner regions of an accretion disk around a supermassive black hole can reach temperatures of billions of degrees, hotter than the center of any star, hotter than a supernova explosion, hotter than almost anything else in the universe. At these temperatures, matter glows with incredible intensity. It emits radiation across the entire electromagnetic spectrum, from low-energy radio waves to visible light to ultraviolet radiation to high-energy X-rays and gamma rays. The accretion disk becomes a beacon, a lighthouse of radiation visible across billions of light years. The energy released as matter falls into a black hole is staggering in its efficiency. When you drop an object into a black hole's gravitational field, up to 40% of its mass can be converted directly into energy, according to Einstein's famous equation E = mc squared. Compare this to nuclear fusion, the process that powers stars, which converts less than 1% of mass into energy. Black hole accretion is the most efficient energy generation mechanism known to physics, and when a black hole is feeding actively, when it has abundant material to consume, it becomes a source of light and radiation beyond anything else in nature. Above the accretion disk, there exists a region of even more extreme physics called the corona. This is a cloud of superheated plasma, electrons stripped from their atoms and accelerated to nearly the speed of light, producing intense X-ray radiation. The corona is one of the least understood parts of black hole physics, its exact structure and behavior still debated among researchers, but its signature, a characteristic pattern in the X-ray light from active black holes, is one of the key ways we identify and study these objects from across the universe. And then there are the jets. When a supermassive black hole is feeding heavily, when its accretion disk is thick with infalling matter, something truly spectacular can happen. Twisted magnetic field lines, wound up by the rotating black hole and its spinning disk, can channel some of the infalling material outward at nearly the speed of a light. These relativistic jets are cosmic blowtorches, beams of particles and radiation that can extend for millions of light years, far beyond the galaxy that contains the black hole. The jets from our galaxy-eating black hole are longer than the diameter of the Milky Way, streams of matter and energy that heat the intergalactic medium and suppress star formation in neighboring galaxies millions of light years away. Now that we understand the physics, let us meet our monster. Let us introduce the specific black hole that has earned the terrifying title of Galaxy Eater. The object we are discussing has been observed by virtually every major telescope humanity has pointed at the sky. Radio telescopes have mapped its jets extending across millions of light years. X-ray observatories have measured the searing radiation pouring from its corona. Optical and infrared telescopes have captured the light of its accretion disk, light so bright that it completely overwhelms the combined light of all the hundreds of billions of stars in its host galaxy. This black hole, residing at the heart of a distant active galaxy, represents one of the most extreme examples of supermassive black hole activity ever observed. The mass of this object is estimated at somewhere between 10 and 40 billion solar masses, placing it firmly in the ultramassive category. To put this in perspective, our own galaxy's central black hole, Sagittarius A star, has a mass of 4 million suns. The Galaxy Eater is at least 2,500 times more massive, possibly 10,000 times more massive. If Sagittarius A star is a house cat, the Galaxy Eater is a blue whale. If our black hole is a pond, this one is an ocean. The scale is almost impossible to truly comprehend. The event horizon of this black hole, the point of no return, has a radius estimated at over 100 billion kilometers. That is more than 3 times the distance from the Sun to Neptune, the outermost major planet in our solar system. Our entire solar system from the Sun to the Kuiper Belt could fit within the event horizon with room to spare. If you were falling toward this black hole, traveling at the speed of light, it would take you over 4 days to fall from the event horizon to the singularity. 4 days of falling into darkness, 4 days during which you could contemplate your fate, knowing that no force in the universe could save you. The host galaxy of this black hole is, or was, a massive elliptical galaxy, a spherical collection of hundreds of billions of ancient stars. But it is no longer the galaxy it once was. The central black hole has been actively feeding for millions of years, possibly tens of millions of years, and its influence has fundamentally transformed the galaxy around it. The central regions have been cleared of gas, the raw material needed to form new stars. The jets have heated the remaining gas to temperatures too high for it to cool and collapse into stellar nurseries. The galaxy is being sterilized from the inside out, its capacity to create new stars destroyed by the very object at its heart. I need you to pause for a moment and consider what this means. We are not talking about a few stars being destroyed, not a few solar systems being consumed. We are talking about an entire galaxy, a structure containing more stars than there are grains of sand on all the beaches of Earth, being fundamentally transformed, perhaps destroyed, by a single object at its center. This is cosmic violence on a scale that makes every war ever fought on Earth, every natural disaster, every extinction event look like a minor inconvenience. And it is happening right now, unfolding over timescales so vast that human civilization is merely a brief flash, a single frame in a movie that runs for millions of years. The feeding rate of this black hole is almost incomprehensible. Observations suggest it is consuming matter at a rate of roughly 1 to 10 solar masses per year. That means every year that passes, material equivalent to 1 to 10 entire suns is being heated, torn apart and swallowed into the abyss. At 1 Earth mass per second, which is within the estimated range for the most extreme feeding episodes, this black hole consumes the equivalent of our entire planet, faster than you can say the words. Every hour it eats more than Jupiter. Every day it consumes more than 3,000 Earth masses. Every month, nearly 100,000 Earths. And this has been going on for millions upon millions of years. The energy released by this process is equally staggering. The luminosity of this black hole system, the rate at which it is releasing energy into space, is estimated at several 100 trillion times the luminosity of our Sun. That is more light than 1 trillion suns, more energy than the combined output of our entire Milky Way galaxy. All of this power is coming from a region smaller than our solar system, a cosmic engine of almost unimaginable efficiency. If we could somehow capture the energy being released by this black hole for just 1 second, it would be enough to power human civilization at its current rate for trillions of years. Alright, if you are still with me, if your mind is properly blown by the scale of what we're discussing, I want to take a moment. Take a breath. Let the enormity of it sink in. We are talking about forces and energies and scales that our brains simply did not evolve to comprehend. We evolved to understand the physics of throwing rocks and avoiding predators, not to intuitively grasp objects with the mass of 10 billion suns consuming matter at the rate of 1 Earth per second. If you are enjoying this journey to the extremes of the cosmos, if this kind of content is what you want to see more of, take a second to smash that like button. It helps the algorithm understand that people want to learn about these incredible cosmic phenomena, and it helps more people discover this video. And if you have not subscribed yet, join our community. We explore the strangest, most fascinating, most mind-bending aspects of the universe, and I would love to have you along for the ride. Now let us go deeper. Let us examine exactly what is being consumed by this cosmic monster. Because the answer reveals a cosmic tragedy playing out over millions of years. The primary food source for supermassive black holes is interstellar gas. Galaxies are not empty spaces between stars. They are filled with diffuse clouds of hydrogen and helium, the primordial elements formed in the Big Bang, along with heavier elements produced in generations of stellar explosions. This gas is the raw material from which new stars form, the lifeblood of a galaxy's future. In a galaxy with an actively feeding central black hole, this gas becomes fuel for the beast. Gravity pulls the gas toward the galactic center. As it falls inward, it joins the accretion disk, that swirling maelstrom of superheated matter orbiting the event horizon. The gas is heated, ionized, torn apart at the molecular level, and gradually spirals inward until it crosses the point of no return. A typical massive galaxy might contain billions of solar masses worth of interstellar gas. The galaxy eater has been consuming this gas for so long that the central regions are becoming depleted. Future generations of stars that might have formed from this gas will now never exist. The galaxy's future is being stolen, one solar mass at a time. But gas is not the only thing being consumed. Stars themselves fall prey to this cosmic predator, and when they do, the results are spectacular and terrible. When a star passes too close to a supermassive black hole, it experiences what astronomers call a tidal disruption event. The gravitational force on the side of the star closest to the black hole is significantly stronger than the force on the far side. This difference in gravitational pull, the tidal force, can become so extreme that it exceeds the star's own self-gravity, the force holding the star together. When this happens, the star is torn apart. It does not explode like a supernova. It is stretched, pulled like taffy, elongated into a stream of stellar material that wraps around the black hole. Astronomers have called this process spaghettification, a somewhat whimsical name for an incredibly violent process. Imagine a star like our Sun, a sphere of hot plasma 1.4 million kilometers in diameter, being stretched into a thin stream millions of kilometers long, then billions of kilometers long, wrapping around a black hole and being gradually consumed over the course of months or years. The light from these events can be seen from across the universe. Brief flares that announce the death of a star that wandered too close to a monster it could not comprehend. How many stars has the galaxy eater consumed? This is a difficult question to answer precisely, but we can make estimates. Based on the stellar density in the galaxy's core and the rate at which stars should be scattered onto black hole crossing orbits, the consumption rate could be one star every few thousand to every few tens of thousands of years. Over the millions of years that this black hole has been actively feeding, it could have consumed thousands or even tens of thousands of stars, each one a potential solar system, each one possibly harboring planets, maybe even life, all consumed, transformed into radiation, and a tiny addition to the black hole's mass. But the consumption goes beyond individual stars. Entire star systems fall into the abyss, planets that orbited those doomed stars, moons that orbited those planets, asteroids and comets, and all the debris of solar system formation. None of it escapes. The tidal forces that tear apart a star would shred a planet even more easily, reducing solid rocky worlds to streams of rubble before final consumption. Gas giant planets would be stripped of their atmospheres, their cores exposed and destroyed. In the far reaches of these doomed systems, comets that had orbited peacefully for billions of years would find their orbits perturbed, some flung into interstellar space, others sent plunging toward the central fire. And there is another form of black hole feeding, one that represents cosmic violence on the most extreme scale. Black holes can consume other black holes. When galaxies merge, as they frequently do over cosmic time, their central black holes are brought together. They spiral toward each other over millions of years, their gravitational interaction creating waves in the fabric of space-time itself. These gravitational waves, predicted by Einstein a century ago and first directly detected in 2015, carry energy away from the system, causing the black holes to spiral closer and closer together. Finally, in a cataclysmic merger lasting only fractions of a second, the two black holes combine into one, releasing more energy in gravitational waves than all the stars in the observable universe are producing in light at that moment. The galaxy eater has almost certainly consumed other black holes in its history. Its enormous mass, far beyond what gas accretion alone could easily produce, suggests a history of mergers. Smaller black holes from satellite galaxies absorbed over billions of years, intermediate black holes from dense star clusters at the galaxy's center, all adding to the monster's mass. Each merger would have been accompanied by a burst of gravitational waves, a signal that rippled outward through the universe at the speed of a light, a cosmic announcement of violence on a scale that dwarfs anything we can directly observe. Let me walk you through the mathematics of destruction, because the numbers themselves tell a story of almost unimaginable violence. When matter falls into a black hole, a portion of its mass is converted to energy according to Einstein's equation, E equals mc squared. The speed of light squared is an enormous number, roughly 9 times 10 to the 16th meters squared per second squared. This means that even a small amount of mass contains enormous energy. 1 kilogram of matter, fully converted to energy, would release 90 quadrillion joules, roughly the energy of a 20 megaton nuclear weapon. Black hole accretion does not convert 100% of mass to energy, but it is remarkably efficient. For a rapidly spinning black hole, up to 40% of the mass of infalling material can be converted to radiation and kinetic energy in jets before the remainder disappears below the event horizon. For the galaxy eater consuming perhaps 10 solar masses of material per year, at even 30% efficiency, the energy release is approximately 1 times 10 to the 47 joules per year. To put this in perspective, our entire sun produces about 1 times 10 to the 34 joules per year. The galaxy eater, from its accretion process alone, releases more energy than 1 trillion suns. The temperatures involved are equally extreme. The inner regions of the accretion disk, where material is orbiting just a few event horizon radii from the black hole, reach temperatures of 100 million to 1 billion Kelvin. The corona, that mysterious region of superheated plasma above the disk, can reach temperatures of 100 billion Kelvin. These are temperatures at which the very nature of matter changes, where atoms cannot exist, where even atomic nuclei struggle to remain intact, where the physics approaches conditions seen only in the first moments after the Big Bang. The jets, those relativistic beams of matter and energy shooting outward from the black hole's poles, reach speeds of 99% the speed of light or more. At these speeds, the effects of special relativity become dramatic. Time passes more slowly for particles in the jet compared to the rest of the universe. The jets are carrying matter and energy outward at rates that, for the most powerful examples, rival the entire energy output of the accretion disk, and they maintain this power over distances of millions of light years, shaping the intergalactic medium and influencing the evolution of matter that has never even been inside the host galaxy. How do we know all of this? How can astronomers sitting on a small planet orbiting an ordinary star in a typical spiral galaxy make confident statements about objects billions of light years away? The answer lies in the power of multi-wavelength astronomy and the fundamental physics of light. Every time matter does anything at all, it produces characteristic signatures in the electromagnetic radiation it emits. By analyzing that radiation, we can determine temperatures, densities, compositions, velocities, magnetic field strengths, and countless other properties of distant objects. Radio telescopes, enormous dishes and arrays of dishes spread across continents, or even the entire Earth, detect the longest wavelengths of electromagnetic radiation. They reveal the jets of supermassive black holes, tracing streams of relativistic particles extending far beyond the visible boundaries of galaxies. The synchrotron radiation produced when electrons spiral around magnetic field lines in these jets has a distinctive spectrum that tells us about the jet's power, its magnetic field strength, and its interaction with the surrounding medium. X-ray telescopes, necessarily placed in space because Earth's atmosphere blocks X-rays, detect the highest energy radiation from hot gas near the event horizon. The Chandra X-ray Observatory and the XMM Newton satellite have revealed the corona and inner accretion disk of countless active black holes, measuring temperatures of hundreds of millions of degrees and detecting the signatures of matter spiraling into oblivion. X-ray observations can even measure the spin of distant black holes by analyzing how the accretion disk's light is modified as it escapes from the extreme gravitational field. Optical and infrared telescopes, both ground-based and space-based, capture the light of accretion disks across a broader range of wavelengths. The Hubble Space Telescope has imaged the host galaxies of distant quasars, revealing the galactic environments in which these monster black holes reside. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is now probing the most distant active black holes in the universe, objects whose light has traveled for more than 13 billion years to reach us, showing us supermassive black holes that existed when the universe was less than 1 billion years old. Gravitational wave detectors, the newest tool in our astronomical arsenal, detect not electromagnetic radiation, but ripples in the fabric of space-time itself. LIGO and Virgo have detected dozens of black hole mergers, most involving stellar mass black holes but some hinting at objects in the intermediate mass range. Future space-based detectors like LISA will be sensitive to the gravitational waves from supermassive black hole mergers, allowing us to directly observe the most violent events in the post-Big Bang universe. By combining observations across all these wavelengths and detection methods, astronomers build a comprehensive picture of objects like our galaxy eater. No single observation tells the whole story, but together they reveal the mass, the feeding rate, the jet power, the influence on the host galaxy, and the position in cosmic history of these extreme objects. It is a triumph of human curiosity and ingenuity that we can know so much about something so distant and so extreme. Now we must consider the consequences. What does it mean for a galaxy to have a voraciously feeding supermassive black hole at its center? The effects are profound, transformative, and ultimately catastrophic for the galaxy as a stellar system. The most immediate effect is in the very center of the galaxy, within a few hundred light-years of the black hole. This region is essentially a death zone. The radiation from the accretion disk is so intense that it would sterilize any planet, destroying organic molecules and stripping away atmospheres. The gravitational tides are strong enough to disrupt planetary orbits and eventually stars themselves. Any civilizations that might have existed in this region, perhaps orbiting stars that wandered too close to the center, would have been destroyed millions of years ago. Their worlds either consumed directly or rendered uninhabitable by the radiation bath. But the black hole's influence extends far beyond this immediate death zone. The jets, those relativistic outflows carrying matter and energy at nearly the speed of light, inject enormous amounts of heat into the galaxy's gas supply. This process, called AGN feedback, is one of the most important factors in galaxy evolution. When gas is heated, it cannot cool and collapse to form new stars. The jets from our galaxy eater have been heating the gas in its host galaxy for millions of years, effectively preventing star formation across a significant fraction of the galaxy's volume. This is why we can say the black hole is eating its galaxy. It is not just consuming stars and gas directly, though it is doing that too. Or it is destroying the galaxy's ability to produce new stars, cutting off its future. A galaxy that cannot form new stars is a galaxy that is dying. The existing stars will continue to shine for billions of years, slowly aging and eventually fading, but no new stars will replace them. The galaxy will grow dimmer and redder over cosmic time, a stellar graveyard maintained by the monster at its heart. The morphology of the galaxy, its physical structure and shape, is also being transformed. Galaxies naturally come in several types: spirals like our Milky Way, ellipticals that are more spherical, and irregulars with no defined structure. The process of active black hole feeding, combined with the merger history that likely led to such a massive central object, tends to transform galaxies from spirals into ellipticals. The beautiful spiral arms maintained by ongoing star formation and galactic rotation fade as star formation ceases and dynamical processes randomize stellar orbits. The host galaxy of our black hole, if it was ever a spiral, is now a giant elliptical, a smooth, featureless blob of ancient stars. Neighboring galaxies are not immune to these effects. The jets from our galaxy eater extend for millions of light years, far beyond the optical boundaries of the host galaxy. Where these jets encounter the intergalactic medium, they create enormous shock waves, heating gas to temperatures of hundreds of millions of degrees. This hot gas forms halos around the jet paths, visible in X-ray observations as elongated structures extending across vast distances. Any small galaxies unfortunate enough to lie in the jet's path can have their gas supplies heated and stripped away, their own star formation quenched by the distant influence of a black hole in another galaxy entirely. What is the timeline of this destruction? The active feeding phase we're observing has likely been going on for at least several million years, possibly tens of millions of years. This is based on the length of the jets and the time it would take material traveling at nearly light speed to reach their current extent. The black hole will continue feeding as long as there is material available in the accretion disk and a supply of gas and stars falling inward from the galaxy to replenish it. This could continue for tens of millions of years more, or the feeding could slow down as the available fuel supply diminishes. Looking further ahead, we can project what the galaxy will look like at various points in the future. In 100 million years, assuming current conditions continue, the central regions of the galaxy will be almost completely cleared of gas. Star formation will have effectively ceased across the entire galaxy. The jets may have extended even further, heating an even larger volume of intergalactic space. In 500 million years, the galaxy will have settled into a quiescent state. The black hole, having exhausted the readily available fuel supply, will be essentially dormant, like our own galaxy's central black hole is today. But unlike our Milky Way, This galaxy will have no significant gas reserves, no capacity to form new stars. It will be aging, its stellar population slowly growing older and dimmer. In 1 billion years and beyond, the galaxy will be a relic. Its brightest stars will have all died, leaving behind only the long-lived low-mass stars, dim red dwarfs that can burn for trillions of years but provide little light. The galaxy will be dimmer, redder, a shadow of what it might have been if not for the ravenous hunger of its central black hole. This is the fate of the Galaxy Eater's host, a fate that it shares with many massive galaxies in the universe that experience similar episodes of intense black hole activity in their pasts. At this point in our journey, I want to pause and acknowledge the scale of what we are contemplating. We have been talking about destruction on a level that makes human concern seem microscopic, galactic sterilization playing out over millions of years, the death of stellar nurseries, the transformation of a galaxy from a vibrant producer of new stars into a static relic. I am curious how you are feeling about all of this. Does contemplating cosmic violence on this scale fill you with awe, with terror, with a strange peace at the recognition of our cosmic insignificance? Drop a comment letting me know, because I think how we emotionally respond to the universe's indifference says something important about who we are as a species, and if you're still watching, you are clearly someone who is not afraid to grapple with big ideas. Consider subscribing if you have not already, because we're going to go even deeper into the physics and implications of galaxy-eating black holes. Now let us dive into the deep physics, the fundamental science that makes all of this possible. To truly understand black holes, we must understand general relativity, Albert Einstein's revolutionary theory of gravity published in 1915. Before Einstein, we understood gravity through Newton's law of universal gravitation, a mathematical description that worked extraordinarily well for predicting the motions of planets and falling apples, but provided no explanation for why gravity exists or what it actually is. Einstein changed everything. According to general relativity, gravity is not a force in the traditional sense. It is a consequence of the curvature of space-time. Mass and energy cause space-time to curve, and objects moving through curved space-time follow paths that appear to us as gravitational attraction. The classic analogy is a heavy ball placed on a stretched rubber sheet, causing a depression that makes nearby smaller balls roll toward it. But this analogy is imperfect because it only shows curvature in 2 dimensions of space, while general relativity describes curvature in 4-dimensional space-time, 3 dimensions of space plus 1 of time. The mathematics of general relativity is expressed through the Einstein field equations, a set of 10 interrelated differential equations that describe how matter and energy determine the curvature of space-time, and how that curvature influences the motion of matter and energy. These equations are notoriously difficult to solve, but certain special cases have exact solutions. One of the most important is the Schwarzschild solution, found by Carl Schwarzschild just months after Einstein published his theory, while Schwarzschild was serving on the front lines in World War I. The Schwarzschild solution describes the space-time around a spherical non-rotating mass, and it contains within it the prediction of black holes. The Schwarzschild radius, the radius at which the event horizon of a non-rotating black hole would be located, is given by 2 times the gravitational constant times the mass divided by the speed of light squared. For the Sun, this works out to about 3 kilometers. For our Galaxy Eater, with a mass of 10 billion suns or more, the Schwarzschild radius is over 30 billion kilometers. But real astrophysical black holes almost certainly rotate, and rotating black holes are described by a different solution, the Kerr solution found by Roy Kerr in 1963. A Kerr black hole is more complicated than a Schwarzschild black hole. Instead of a single spherical event horizon, it has 2 horizons, an outer event horizon and an inner Cauchy horizon. The singularity at the center is not a point but a ring, and most importantly for the physics of accretion and jets, a rotating black hole drags space-time around with it, an effect called frame dragging, or the lens-thirring effect. Near a rapidly spinning black hole, space-time itself rotates, and anything within a region called the ergosphere is forced to co-rotate with the black hole, even light. This frame dragging is believed to be crucial for the formation of relativistic jets. The rotation of the black hole, combined with the magnetic field lines threading the accretion disk and event horizon, can extract rotational energy from the black hole and convert it into the kinetic energy of outflowing matter. This is the Blanford-Zinayak process. named after the physicists who first proposed it in 1977. A rapidly spinning black hole is not just a passive sink for matter and energy, it can actively power outflows by surrendering some of its own rotational energy. There is an even more exotic way to extract energy from a rotating black hole, the Penrose process. This relies on a property of the ergosphere, the region outside the event horizon, where frame dragging is strong enough that nothing can remain stationary relative to distant stars. Within the ergosphere, it is possible for a particle to have negative energy relative to observers far from the black hole. If a particle falls into the ergosphere and splits into two pieces, with one piece falling into the black hole with negative energy and the other escaping, the escaping piece can carry away more energy than the original particle had. The energy comes from the black hole's rotation, slowing it down slightly. This is purely theoretical for now as far as we know, but it demonstrates that black holes are not just cosmic vacuum cleaners, they are reservoirs of extractable energy. What happens to information that falls into a black hole? This is one of the deepest questions in theoretical physics, known as the black hole information paradox. According to quantum mechanics, information is never truly destroyed. The quantum state of any system can in principle be evolved forward or backward in time, meaning that information about the past state of a system is always preserved in its current state. But according to classical general relativity, anything that falls into a black hole is lost forever, hidden behind the event horizon and eventually crushed into the singularity. Stephen Hawking made this paradox more acute in 1974 when he discovered that black holes are not truly black. Due to quantum effects near the event horizon, black holes emit radiation, now called Hawking radiation. This radiation causes the black hole to lose mass over time, and eventually, over incomprehensibly long timescales, the black hole would evaporate completely. But the Hawking radiation appears to be thermal, random, containing no information about what fell into the black hole. If the black hole evaporates completely, where does the information go? This paradox has driven some of the most creative theoretical physics of the past half-century. Current thinking, supported by developments in string theory and the ADS/CFT correspondence, thus suggests that the information is somehow encoded in the Hawking radiation, though in such a scrambled form that it would be practically impossible to recover. The details remain controversial, and the resolution of the information paradox may require a complete theory of quantum gravity that we do not yet possess. For our galaxy eater, Hawking radiation is completely negligible. The temperature of Hawking radiation is inversely proportional to the black hole's mass, meaning that more massive black holes are colder. A black hole of 10 billion solar masses would have a Hawking temperature of about 6 times 10 to the negative 18th Kelvin, colder than the cosmic microwave background radiation by a factor of nearly 1 billion. At this temperature, the black hole absorbs more energy from the cosmic microwave background than it loses to Hawking radiation, meaning it is actually gaining mass from this effect rather than losing it. Hawking evaporation would only become relevant in the incredibly distant future, after the universe has expanded and cooled for eons beyond the current age. There is another limit on black hole feeding that turns out to be crucial for understanding our galaxy eater. The Eddington Limit, named after the British astrophysicist Arthur Eddington, is the maximum rate at which a spherical object can accrete matter while still maintaining hydrostatic equilibrium. The idea is straightforward. Infalling matter releases radiation. That radiation exerts an outward pressure on the infalling matter. If the radiation pressure exceeds the gravitational attraction, the infalling matter is pushed away and accretion stops. For a typical supermassive black hole accreting in a spherically symmetric manner, the Eddington limit sets a maximum growth rate that would allow the black hole to roughly double its mass in about 50 million years. Many observed active galactic nuclei and quasars appear to be radiating at or near their Eddington limit, suggesting their black holes are growing as fast as this simple model allows. But our galaxy eater appears to sometimes exceed this limit. This is possible because the Eddington limit assumes spherical symmetry, which is not the case for a disk-shaped accretion flow. In a disk geometry, radiation can escape more easily in the vertical direction, while matter continues to flow inward through the disk. This allows for super-Eddington accretion, a regime where black holes can grow faster than the simple Eddington argument would suggest. Super-Eddington accretion is associated with some of the most luminous quasars in the universe, and may be necessary to explain how supermassive black holes grew so large so quickly in the early universe. The relativistic effects near the event horizon of a supermassive black hole are extreme and counterintuitive. Time dilation, one of the most famous predictions of relativity, becomes dramatic. To a distant observer, time appears to pass more and more slowly for objects approaching the event horizon, appearing to freeze at the horizon itself. This is not an illusion. It is a genuine effect of the curvature of space-time. A clock falling toward the black hole would tick normally from its own perspective, but would appear to tick slower and slower from our distant vantage point. If you were falling into a supermassive black hole like our Galaxy Eater, the experience would be profoundly strange. Because the black hole is so large, the tidal forces at the event horizon would actually be quite gentle. You could cross the event horizon without being torn apart, unlike the case for stellar mass black holes where tidal forces would spaghettify you well before reaching the horizon. But once you crossed the event horizon, you would be doomed. Every possible path through space-time would lead toward the singularity. You could fire your rockets, you could turn around, you could move at any speed in any direction, and you would still find yourself inexorably approaching the center. The singularity would be in your future the way tomorrow is in your future, inescapable and inevitable. From outside, watching someone fall into the black hole, you would see something equally strange. Their image would grow redder and dimmer as the light they emit is progressively redshifted by the gravitational field. Time would appear to slow down for them, their motions becoming sluggish, their clock almost freezing. You would never actually see them cross the event horizon. Their image would fade toward infinite redshift and zero brightness, becoming forever frozen from your perspective at the edge of the point of no return. This is why early physicists called black holes frozen stars, because from the outside, infalling matter appears to freeze at the horizon. How does our Galaxy Eater compare to other supermassive black holes we have observed? Let us put it in context with some of the most famous and extreme black holes known to science. The supermassive black hole at the center of the galaxy M87, the first ever to be imaged directly by the Event Horizon Telescope, has a mass of about 6.5 billion solar masses. This is a titan by any measure, one of the most massive black holes in the relatively nearby universe. But our Galaxy Eater potentially exceeds this by a factor of several, making M87's black hole look almost modest by comparison. M87's black hole also has prominent jets, visible in radio and optical images extending thousands of light-years from the galaxy's center, but it's currently in a much less active state than our Galaxy Eater. Then there is TON 618, long held as one of the most massive black holes known. Located about 10 billion light-years away, TON 618 powers an enormously luminous quasar with an estimated black hole mass of around 66 billion solar masses. This is so massive that its event horizon would have a diameter comparable to the distance from the Sun to Pluto multiplied by 4. TON 618 represents the extreme upper end of the black hole mass function, and our Galaxy Eater, while enormously massive, is still smaller than this behemoth. In recent years, an even more extreme object has been discovered. Phoenix A, the black hole at the center of the Phoenix Cluster's central galaxy, has been estimated at around 100 billion solar masses, though estimates vary and the uncertainties are large. If this estimate is correct, Phoenix A would be the most massive black hole ever discovered, a true ultramassive black hole at the very limits of what theory suggests is possible. The Phoenix Cluster black hole is also notable for being surrounded by one of the strongest cooling flows ever observed, with enormous amounts of gas cooling and potentially feeding the black hole, though at a rate that appears to be regulated by feedback from the black hole's jets. At the other extreme, we have our own Sagittarius A star, the supermassive black hole at the center of the Milky Way. With a mass of only 4 million solar masses, Sagittarius A star is relatively modest among supermassive black holes. It is also extremely quiet, accreting matter at a rate far below its Eddington limit, emitting a tiny fraction of the radiation produced by actively feeding black holes. If Sagittarius A star were accreting at the rate of our Galaxy Eater, its radiation would be visible in the daytime sky, and the Earth would be bathed in X-rays. We are fortunate that our galaxy's central black hole is currently dormant. What makes the Galaxy Eater particularly interesting is not just its mass but its activity level. Many supermassive black holes, probably most, spend much of their time in a quiet state like Sagittarius A star. Active feeding episodes are transient events triggered by an influx of gas, perhaps from a galaxy merger, a disruption of gas flows within the galaxy, or some other perturbation. Our galaxy eater represents a snapshot of a supermassive black hole in its most violent phase, a period that may last tens of millions of years but is still brief on cosmic timescales. Now we come to the question that I know many of you have been wondering about. Could this happen to us? Could the supermassive black hole at the center of our Milky Way wake up and begin consuming our galaxy? The short answer is yes, it could happen, but probably not for billions of years, and even then it would be very different from what we observe in our distant galaxy eater. Sagittarius A* is currently quiet because it lacks a substantial supply of fuel. The gas in the Milky Way's central region is not flowing inward at a high rate, and the stars near the black hole are not being scattered into it frequently enough to maintain active accretion. But this situation will not last forever. In approximately 4 to 5 billion years, the Milky Way is expected to collide and merge with the Andromeda Galaxy, the large spiral galaxy that is currently approaching us at about 110 kilometers per second. Galaxy mergers are chaotic events. As the two galaxies interpenetrate, gravitational interactions will disrupt the orderly motion of stars and gas. Gas clouds from the two galaxies will collide, lose angular momentum and flow toward the merged system's center. Both supermassive black holes, the Milky Way's Sagittarius A* and Andromeda's central black hole, which has a mass of about 100 million solar masses, will sink toward the center of the merged galaxy and eventually merge themselves. During this process, there will likely be periods of active accretion. The influx of gas from the merger could trigger quasar-like activity from one or both black holes. The merged black hole, after the two objects combine, will likely go through its own active phase as it consumes the gas driven to the center by the merger. For millions of years, the merged galaxy, sometimes called Milkomeda, could have an actively feeding supermassive black hole at its center, complete with high luminosity and possibly jets. Would this be dangerous for any life that might still exist on Earth at that time? Possibly. The Sun will have long since burned through its hydrogen and become a red giant, likely destroying or engulfing the Earth, so our planet specifically would not be at risk. But any life that might have developed elsewhere in the galaxy, or on other planets that humans or our descendants might have colonized, could be affected by the increased radiation from an active galactic nucleus. The central regions of the galaxy would be bathed in X-rays and gamma rays. The jets, if they developed, could create hazardous conditions along their paths. A galaxy merger is not a gentle process, but there is good news too. Even during an active phase, the dangerous region around a supermassive black hole is relatively small on galactic scales. The Sun's position, about 26,000 light-years from the galactic center, would be relatively safe from the direct effects of even a powerfully feeding black hole. Cosmic ray fluxes might increase, and there could be some atmospheric effects from increased ultraviolet radiation, but the direct X-ray and gamma-ray flux would be reduced by distance to manageable levels. Life on a planet similar to Earth at the Sun's current distance from the galactic center would probably survive an active galactic nucleus phase, though conditions might become somewhat harsher. The probability of a truly galaxy-eating event like we observe in our distant object is lower. That requires a very massive black hole, a very large gas supply, and conditions that maintain active feeding for millions of years. The Milky Way-Andromeda merger will produce a large elliptical galaxy, but the total gas supply and the mass of the resulting black hole will likely be lower than in the most extreme cases. We would probably see quasar-like activity, but perhaps not the sustained ultra-luminous feeding of the most extreme galaxy eaters. On the timescales of human civilization, we are completely safe. The Andromeda merger is billions of years in the future. Sagittarius A* is quiet and will remain so for the foreseeable future. The nearest actively feeding supermassive black hole is millions of light-years away. SUS is far too distant to have any effect on Earth. The galaxy eaters we observe are cosmic phenomena to study and wonder at, not threats to fear. Let me tell you about the most recent scientific findings regarding galaxy-eating black holes and related phenomena, because our understanding is constantly evolving as new observations come in. Over the past few years, a combination of new telescope capabilities and innovative analysis techniques has revealed surprising facts about how supermassive black holes interact with their host galaxies. The James Webb Space Telescope, operational since 2022, has been particularly revolutionary. Its infrared sensitivity allows it to observe the most distant active black holes, including quasars from when the universe was less than 1 billion years old. These observations have revealed supermassive black holes that seem impossibly large given how little time they had to grow. Some of these early black holes have masses of over 1 billion solar masses existing less than 700 million years after the Big Bang. This presents a puzzle. How could black holes grow so massive so quickly? Several theories have been proposed. Perhaps these black holes formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar black hole stage entirely and forming with masses of tens of thousands to hundreds of thousands of solar masses from the start. Perhaps they grew through sustained super Eddington accretion, feeding faster than the simple Eddington limit would suggest. Perhaps they accumulated mass through frequent mergers with other black holes in the crowded early universe. Current research is actively investigating these possibilities, and the answer may involve some combination of all three. Ground-based radio telescope arrays have also made remarkable progress. The Event Horizon Telescope collaboration, which produced the first image of a black hole shadow in 2019, has continued to refine its techniques and expand its network of telescopes. The images of both M87's black hole and our own Sagittarius A star reveal the extreme gravitational lensing of light near the event horizon, providing direct visual confirmation of general relativity's predictions in the strongest possible gravitational fields. X-ray observatories continue to monitor active galactic nuclei across the sky, tracking changes in their accretion rates over time. These observations reveal that black hole feeding is not steady, but varies on timescales from hours to years. Some of this variability is due to instabilities in the accretion disk, while some may be due to individual objects, stars, or dense gas clouds, passing through and temporarily increasing the accretion rate. By studying these variations, astronomers can probe the structure of accretion disks and the environments immediately surrounding supermassive black holes. Gravitational wave astronomy is poised to open a new window on supermassive black hole physics. While current ground-based detectors like LIGO and Virgo are sensitive to stellar mass black hole mergers, the planned Laser Interferometer Space Antenna, or LISA, will be sensitive to much longer gravitational wave wavelengths, the kind produced by supermassive black hole mergers. LISA, expected to launch in the mid-2030s, will be able to detect supermassive black hole mergers out to the edge of the observable universe, providing direct information about how these objects grow through cosmic time. Pulsar timing arrays, networks of precisely timed radio pulsars across the Milky Way, have recently detected what appears to be a background of gravitational waves permeating the universe. This background is believed to come from the combined signals of many supermassive black hole binaries, slowly spiraling together across cosmic time. The detection confirms that supermassive black hole mergers are common in the universe's history and provides constraints on how often these events occur. There remain many open questions. We still do not fully understand how supermassive black holes first formed in the early universe. We do not have a complete theory of jet formation, or the exact mechanism that produces the ultra-relativistic speeds observed. The inner structure of accretion disks, especially in the poorly understood regime of super Eddington accretion, remains uncertain. The connection between black hole activity and star formation in host galaxies, the feedback process that determines whether a galaxy lives or dies, is still being mapped out in detail. These are the frontiers of current research. Thousands of astronomers around the world, using the most sophisticated telescopes ever built, are working to answer these questions. Every year brings new discoveries, new surprises, and new revisions to our understanding. The story of galaxy-eating black holes is still being written, and the most exciting chapters may be yet to come. Let us take a moment to contemplate the bigger picture, the cosmic significance of what we have been discussing. Black holes that eat galaxies are not aberrations or monsters in any moral sense. They are natural consequences of the laws of physics operating over cosmic timescales. Gravity, given enough mass in a small enough volume, creates black holes. Accretion, the natural process of matter falling into gravitational wells, feeds them. Angular momentum and magnetic fields, basic physics that we can study in laboratories on Earth, create accretion disks and launch jets. Everything we observe in galaxy-eating black holes follows from the same physics that governs the fall of an apple or the orbit of the moon. In some ways, your supermassive black holes are essential to the universe as we know it. The feedback from active galactic nuclei regulates star formation in massive galaxies, preventing them from converting all their gas into stars in a single burst, and extending stellar activity over billions of years. The jets from supermassive black holes heat the intergalactic medium, affecting the formation of structures across the cosmos. The iron and other heavy elements found in the hot gas of galaxy clusters, products of stellar nucleosynthesis, were distributed by the jets of active black holes in addition to supernova explosions. Without supermassive black holes and their feedback effects, the universe would look very different. There is even speculation that supermassive black holes may have played a role in the conditions that allowed life to exist. By regulating star formation and shaping the chemical evolution of galaxies, black hole feedback may have influenced when and where heavy elements, including the carbon, oxygen, and nitrogen that make up our bodies, became available in sufficient quantities. The iron in your blood and the calcium in your bones were formed in stars, but the distribution of those elements across galaxies was influenced by processes connected to supermassive black holes. We are, in some indirect but real way, shaped by the monsters at the hearts of galaxies. There is something philosophical, perhaps even spiritual, about contemplating these cosmic processes. Human civilizations rise and fall over millennia. Black hole feeding events play out over millions of years. Galaxies evolve over billions of years. The universe itself will continue for timescales that make even galactic evolution seem brief. In this context, what does it mean for a single human life to matter? What significance can our brief existence have against the backdrop of cosmic immensity? I think there are multiple ways to answer this question, and the answer you find most compelling probably depends on your personal worldview. Some find comfort in the idea that our smallness liberates us from cosmic significance, allowing us to focus on meaning in our own lives and relationships without the burden of universal importance. Others find meaning precisely in our ability to comprehend these vast processes, seeing human consciousness as the universe becoming aware of itself, a rare and precious development in the cosmic story. Still others take a purely aesthetic view, finding beauty in the scale and violence of cosmic phenomena without needing to extract personal meaning from them. What I find most remarkable is that we can have this conversation at all. The universe is under no obligation to be comprehensible to beings like us. The laws of physics could have been different, or our brains could have evolved differently, in ways that would make understanding black holes impossible. But instead, we find ourselves on a small rocky planet orbiting an ordinary star, with brains that evolution shaped for survival on the African savanna, somehow capable of grasping the physics of objects billions of light years away. We can write equations that describe the bending of space-time around a black hole. We can build telescopes that gather light that left its source before life crawled out of the ocean. We can understand in detail processes that would destroy us utterly if we were anywhere near them. This is remarkable. This is worth celebrating. Let me take you on an imaginative journey to the Galaxy Eater. Close your eyes if you can, and picture yourself approaching this cosmic monster. You're traveling in some fantastical vessel that can cross the vast gulf of intergalactic space, billions of light years, in moments. As you approach the host galaxy, the first thing you notice is its size. It is a giant elliptical galaxy, a smooth oval of light containing hundreds of billions of stars. But something is wrong. The center is too bright, a brilliant point that outshines everything around it, a nuclear furnace of radiation pouring out into space. As you draw closer, details emerge. You see the jets, twin streams of matter and energy extending perpendicular to the galaxy's plane, stretching millions of light years in either direction. They glow with synchrotron radiation, electrons spiraling around magnetic field lines at nearly the speed of light. Where the jets impact the intergalactic medium, there are vast shock waves, bubble-like structures of superheated gas that dwarf the galaxy itself. Closer still, and you begin to see the accretion disk. It is a swirling maelstrom of gas and dust, hundreds of times larger than our solar system, glowing white-hot in the inner regions and cooler red and orange toward the edges. The disk is not uniform. There are bright spots and dark patches, spiral density waves and turbulent eddies, the chaotic physics of magnetized fluid in strong gravitational fields made visible. You notice that space itself seems distorted near the center. Light from background stars is bent and twisted, forming arcs and multiple images as gravitational lensing does its work. The black hole itself is invisible, a region of absolute darkness, but its presence is felt through its effects on everything around it. There is a dark circle at the center of the disk, the shadow of the event horizon, where the black hole's gravity bends light so severely that a region appears dark against the bright background. If you could somehow survive the radiation and venture into the inner regions, time would start to behave strangely. Your clock would tick more slowly compared to someone far from the black hole. Light from the accretion disk would be blue-shifted as you fell inward, then red-shifted as it climbed back out to meet distant observers. Space and time, those fundamental categories of human experience, become flexible, relative, twisted by the presence of so much mass. At the event horizon itself, there is no visible boundary, no wall or barrier. You would simply pass from a region where escape was possible, however difficult, to a region where escape was impossible no matter what you did. And once inside, all paths lead to the singularity. The laws of physics as we understand them predict that you would be crushed to infinite density, though what really happens at the singularity remains one of the great mysteries of physics. This imaginative journey brings the abstract physics to vivid life, but it is more than fantasy. Everything I have described is based on our best scientific understanding. The jets, the accretion disk, the gravitational lensing, the event horizon, all of these are real features of real objects, observed through our telescopes and described by our equations. The universe really does contain such wonders, and we really can know about them from our remote perch on a small planet orbiting an ordinary star. When artists and filmmakers depict black holes, they face the challenge of representing something that is both invisible and visually spectacular. The most famous recent depiction is Gargantua, the black hole in Christopher Nolan's film Interstellar, created in collaboration with physicist Kip Thorne. Gargantua shows many accurate features of spinning black holes, including the distinctive appearance of the accretion disk, which appears to wrap over and under the black hole due to gravitational lensing. Light from the part of the disk behind the black hole is bent over the top and bottom, creating a halo effect that was carefully calculated based on general relativity. However, even Interstellar took some artistic liberties. In reality, an accretion disk around an actively feeding black hole would be tremendously bright and would emit radiation across the electromagnetic spectrum, including deadly X-rays and gamma rays. No spaceship could survive anywhere near an active accretion disk, let alone traverse one as the characters do in the film. The colours in the film were also chosen for visual appeal rather than physical accuracy. A real accretion disk's colours would depend on its temperature structure and the Doppler shifting of light from the rotating disk, producing asymmetries that were not shown in the film. The first real image of a black hole, the famous image of M87's central black hole released in 2019 by the Event Horizon Telescope collaboration, showed something both similar to and different from artistic depictions. The orange ring of light around a dark centre was immediately recognisable as a black hole's shadow, the region where the black hole's gravity prevents light from reaching us. But the image was fuzzy, limited by the resolution of the telescope array, and showed only radio emission rather than the full spectrum of light. It was a triumph of science and engineering, but it also reminded us how much harder it is to observe reality than to imagine it. As we approach the end of our journey, let us consider what ultimately happens to a galaxy-eating black hole. The current feeding frenzy cannot last forever. As the black hole consumes the available gas and disrupts its host galaxy's ability to form new stars, the fuel supply will eventually dwindle. Millions of years from now, perhaps tens of millions of years, the accretion rate will drop. The brilliant quasar-like emission will fade. The jets will weaken and eventually shut off. The black hole will settle into a quiescent state, like our own Sagittarius A star, sleeping at the heart of a galaxy that has been transformed by its hunger. In this quiet phase, which will last for billions of years, the black hole will still be there, still incredibly massive, still warping space-time around it, but it will be essentially invisible, detectable only through its gravitational effects on nearby stars. The host galaxy will age, its stellar population growing older and dimmer. No new stars forming to replace those that die. It will be a red and dead galaxy, a common type in the universe today, many of which experience similar active phases in their pasts. On even longer timescales, the black hole will interact with its environment in more gradual ways. Occasionally a star will wander too close and be tidally disrupted, producing a brief flare of activity. Gravitational interactions with other galaxies might deliver fresh fuel, triggering temporary feeding episodes. Mergers with other galaxies and their central black holes might occur, growing the black hole's mass further. But on the longest timescales, even these events become rare. As the universe expands, galaxies become more isolated, the supply of potential merger partners dwindles, the intergalactic medium thins. Eventually, on timescales of hundreds of billions to trillions of years, galaxies will be lonely islands in an ever-expanding void, their black holes silent and dormant, waiting. What happens to black holes on truly cosmic timescales, after all the stars have burned out and all the gas has been consumed or expelled? This brings us to the speculative frontier of physics, the ultimate fate of black holes in a universe that may last forever. If our current understanding is correct, black holes are not eternal. Hawking radiation, that subtle quantum effect, causes all black holes to slowly evaporate over time. For stellar mass black holes, this evaporation would take about 10 to the 67 years, an incomprehensibly long time. For our galaxy eater, with its mass of 10 billion solar masses, the evaporation time would be even longer, roughly 10 to the 100th years or more. To put these timescales in perspective, the current age of the universe is about 14 billion years, or about 10 to the 10th years. A black hole of 10 billion solar masses would take 10 to the 90th times longer than the current age of the universe to evaporate. These are timescales on which human intuition completely fails. They are longer than any other timescale in physics, longer than the time for protons to decay in many theories, longer than the time for quantum tunneling to gradually dissolve ordinary matter. But eventually, even on these scales, the evaporation would complete. The black hole would shrink, slowly at first, then faster as its temperature increased. In the final moments, as the black hole shrank to microscopic size, it would become incredibly hot. Hotter than any other object in the universe at that time, and it would explode in a final burst of radiation, releasing all its remaining mass as energy. Then it would be gone, leaving nothing behind, a monster that had consumed billions of stars reduced to a whisper of photons dispersing into an empty universe. This is the far future of our galaxy eater. Whatever it consumes now, whatever devastation it wreaks on its host galaxy, whatever jets it launches and whatever gas it heats, in the ultimate end it will evaporate into nothing. The matter it consumed will be returned to the universe as radiation, albeit radiation of such low temperature in the intervening eons that it will barely register above the infinite cold of the far future cosmos. There is something poetically appropriate about this fate. The ultimate equalizer treating the largest structures in the universe the same as the smallest, returning everything to radiation and entropy in the end. We have journeyed together from the basic physics of black holes to the extreme case of a galaxy eater, from the event horizon to the singularity, from accretion disk physics to the far future of cosmic evolution. We have seen how gravity, that most familiar of forces, can create objects so extreme that they challenge our understanding of space, time, and the nature of reality. We have considered what it means for a galaxy to be consumed by its central black hole, the sterilization of star-forming regions, the heating of intergalactic gas, the transformation of a vibrant stellar system into a dead relic. What can we take away from this cosmic horror story? Perhaps a sense of perspective. Human concerns, our politics and economies and personal dramas are important to us and should be important to us. But they exist against a backdrop of cosmic processes that dwarf anything we can directly experience. Somewhere out there, right now, black holes are consuming galaxies, stars are being torn apart, jets of matter are shooting across millions of light years. The universe is doing things on scales and timescales that make our entire recorded history seem like less than the blink of an eye. Perhaps also a sense of wonder. The universe is comprehensible. We, small creatures on a small planet, can understand processes at the extremes of nature. General relativity, written down by Einstein over a century ago, still accurately describes black holes. Quantum mechanics, developed in the early 20th century, predicts Hawking radiation. The tools we have built, radio telescopes and X-ray satellites and gravitational wave detectors, allow us to observe objects billions of light-years away in stunning detail. This is a remarkable achievement of human civilization, and it continues every day as new observations reveal new wonders. Perhaps finally a sense of gratitude. We happen to live at a time and place in the universe where conditions are suitable for life as we know it. Our sun is stable, our planet is at the right distance for liquid water, our solar system is not being bombarded by excessive radiation from an active galactic nucleus. These conditions will not last forever, and they are not universal. Somewhere out there, and worlds that might have harbored life were sterilized by the jets of a feeding black hole. We are fortunate, and perhaps that fortune carries with it some responsibility, to appreciate what we have, to use it wisely, and to seek to understand the universe that gave rise to us. I want to thank you for staying with me through this entire journey into the heart of cosmic darkness. We have covered a lot of ground, from the fundamentals of black hole physics to the specific example of a galaxy-eating monster, from the evidence we use to study these objects to the implications for our own galaxy's future. If you have learned something, if your sense of wonder has been engaged, if you see the night sky a little differently now than you did an hour and a half ago, then I consider this video a success. Now I want to hear from you. What aspect of galaxy-eating black holes do you find most fascinating? What questions do you still have that I did not answer? What topics should we explore in future videos? Drop a comment and let me know. I read every single comment, and your feedback shapes the content I create. If you enjoyed this deep dive into the extreme universe, please like this video. The like button is more than just a number. It tells the algorithm that this kind of content, long-form science education, detailed explanations of complex phenomena, is what people want to see. Every like helps more people discover this video, and every new viewer is someone whose curiosity might be sparked by the wonders of the cosmos. If you have not subscribed yet, now is the perfect time. We explore the strangest, most beautiful, most mind-bending aspects of the universe on this channel. From the smallest quantum phenomena to the largest cosmic structures, from the earliest moments after the Big Bang to the far future, when even black holes have evaporated, we cover it all. Subscribe and hit the bell so you do not miss any of our cosmic adventures, and please, share this video with someone who would appreciate it. Everyone knows someone who loves space, someone who stays up late watching documentaries about black holes, someone who asks big questions about the nature of reality. Share this video with them. Let us build a community of curious minds, people who want to understand the universe we live in. Remember this as you go about your day, as you return to the concerns of ordinary life. You exist in a universe where black holes can eat galaxies. Thine objects with the mass of 10 billion suns consume matter at the rate of 1 Earth per second. Jets of plasma traveling at nearly the speed of light extend across millions of light years. Temperatures reach billions of degrees. Time itself bends and warps near the event horizon. This is the universe you live in. This is the reality you are part of. And yet, here you are, a pattern of matter and energy that somehow became aware of itself. A being that can contemplate black holes and understand accretion physics and feel wonder at the scale of cosmic processes. In a universe of mindless physical processes, you are a mind. In a cosmos that does not care whether it is understood, you seek understanding. That is remarkable. That is worth something. That may be the most improbable and precious thing in all the vast cosmos we have discussed. Thank you for watching. Thank you for your curiosity. Thank you for being part of this community of people who look up at the sky and ask questions. Until next time, stay curious, stay humble before the immensity of the universe, and never stop exploring the cosmic wonders that surround us. End.